In this video, we're going to talk about balancing chemical equations. Now, the law of conservation of mass says that in a chemical reaction, matter cannot be created or destroyed. And our chemical equations must reflect that. And so we have to have the same number and type of each atom on both sides of the equation, right? So we have the reactants on the left. They're separated by an arrow from the products that we draw on the right. And so I have to have all the same number and types of atoms on the reactant side as I do on the product side. The way I like to teach balancing chemical equations is to do it by inspection. Essentially, I go atom by atom and adjust the coefficients in front of each compound until the number of atoms on each side is the same. Now, when I put a coefficient in front of a chemical formula, it applies to all the atoms in that formula. And so we'll do a quick example here, and then I have some tips, and then we'll do several more examples. So when I look at this equation, right, I tend to go atom by atom, right? So I start with potassium, right? I have one potassium on the reactant side, one on the product side, so it's good. Right, I have one chlorine and one chlorine, so it's good. Then I go to the oxygens, and I have three oxygens and two oxygens. And this is a pattern that we'll see very often, right? Generally what we do to balance the atoms is whichever side has the least number of that atoms, I would put a coefficient in front. But there's nothing I can multiply by 2 that's going to give me 3. So the way to get an equal number of oxygens on each side, right? This is sort of like when you're doing lowest common denominators in math, right? What's the smallest common product that's common between the factors 2 and 3? And of course, that's 6. So in order to get to 6, I would put a 3 in front of the O2 here, and then a 2 in front of the KClO3 there. Now, of course, that may mess up the other atoms that were already balanced, but don't worry about that, right? Just do it atom by atom, and if anything, gets unbalanced, we can go back and fix that. Right, so now my oxygens are balanced. I have 2 times 3, I have 6 oxygens on the reactant side. I have 3 times 2, I have 6 oxygens on the product side. So now I would go back, okay, KCl got unbalanced, and now I have to fix it. So I have 2 potassiums now on the reactants. So I want to make 2 potassiums on the products, right? And that also balanced the chlorines, right? Now I have 2 chlorines on the reactants, 2 chlorines on the products, and so it's balanced. Right, so some general tips for balancing chemical equations. First off, we can only change the coefficients when we're balancing an equation. I can put numbers in front of the compounds, giving me, multiple numbers of the compounds, but I can't change the subscripts, right? This 2 in the O2, or I should have made it blue here, but this 3 in the KClO3, right? These subscripts determine the chemical formula. And I can't change the compounds that are present in the equation, so I can't change the subscripts. I can only change the superscripts that go out in front. Right, now, the way I showed to balance chemical equations is by inspection, and so the best way to get good at this is to just practice. And there'll be more practice problems posted on the course D2L site. Right, as I talked about before, I tend to balance the atoms one at a time, right? So don't try to do them all at once because that's just too much going on, right? If you noticed in my explanation in the last slide, right, I just balanced potassiums, then the chlorines, then the oxygens, then I went back and just fixed the potassiums and just fixed the chlorines. I didn't try to kind of do it all at once. If you have an atom that's all by itself, I'll often try to save them for last because very often they're easiest. Because I can balance them without messing up anything else. I also showed you the even and odd mismatches that we had last time, right? A very common pattern you'll see is 2 atoms on one side, 3 on the other, and so we know we've got to make those 6. And in class, we've talked about polyatomic ions, right? When you recognize polyatomic ions, it's often easier if you have the same polyatomic ion on both the products and the reactants. Balance it as a whole unit, right? Balance it as a nitrate or a sulfate rather than, in the case of sulfate, 1 sulfur and 4 oxygens. And then again, the best way to get comfortable, and so you start recognizing some of the similar patterns, is to practice these. All right, one other thing I should mention about these chemical equations, after the chemical formulas, very often we will put the phase that compound is in parentheses. And so a G tells me that it's a gas, L for liquid, S for solid, and then AQ means aqueous, right? So that means that compound is dissolved in water. And a lot of the reactions that we encounter in chemistry and biology involve aqueous reactants or products. And so that's why it has its own special state. All right, so let's look at a couple practice examples, and I'll kind of talk through my thought process that's going on in my head when I'm balancing these. So I'm going to do them one atom at a time. So kind of left to right, I'll often just start with the first atom. So I've got hydrogen first. I have 2 hydrogens on the reactant side, 3 hydrogens on the product side. So this is that 2, 3, or even and odd pattern that we often found. And so the way to get these balanced is if I put a 2 in front of the side that has 3, a 3 in front of that side. Now I have 6 hydrogens on both sides. All right, so then I go to the nitrogen. I have 2 nitrogens, and now I have 2 times 1, so I have 2 nitrogens on the product, and so the nitrogen is also balanced. And so this equation is finished. Okay, here's another one, and this is what I was talking about with the polyatomic ions. Right, so I have a phosphate on the reactants, I have phosphates in the products, I have sulfates in the reactants, and sulfates in the products. And so rather than treating this as a phosphorus and 4 oxygens, I'm going to just treat it as the whole thing together, right? I put the charge there. We're not so worried about the charge when we're balancing, right? But I'm going to balance it as a phosphate, right? So I'm going to treat that thing as if it was, the whole thing, the PO4, as if it was an element, right? And so I have 1 phosphate on the reactant side and 2 phosphates, right? The 2 phosphates on the product side. So to balance those, I'm going to put a 2 in front of the K3PO4. Now I have 2 phosphates on both sides. Right, so now let's do, say, potassium. Right, so I now have 2 times 3. I have 6 potassiums on the reactant side. Right, and I have 2 potassiums on the product side. So to get that up to 6, I'm going to put a 3 here. All right, if we do magnesium next, right, I have 1 magnesium and 3 magnesiums. So to balance that, I'm going to have a 3 in front of the magnesium sulfate. All right, and just like I did with the phosphates, I'm going to treat the sulfates as one thing. So now I have 3 sulfates, and I have 3 sulfates. So I think the sulfates are balanced, right? So we can go back and double check. I've got 6 potassiums, 6 potassiums, 2 phosphates, 2 phosphates. I have 3 magnesiums, 3 magnesiums, 3 sulfates, 3 sulfates, so it's balanced. All right, here's another example. And what I wanted to show on this one is one thing that often happens with oxygen is oxygen shows up a lot in the compounds that we're going to see. And very often oxygen appears in multiple compounds, right? In this case, oxygen is in all 3 compounds in this equation. Very often what you'll find is if you get all the other atoms balanced, the oxygens will just kind of fall into line. Right? If I tried to do the oxygens first, it's like, well, I've got, 4 on this side and I have oxygens in 2 places here. It's like, which ones do I want to try to mess with? And the answer is none of them, right? Do the phosphate and hydrogen first, and then check. And oftentimes what we'll find is the oxygens are sort of balanced themselves when we get everything else balanced. So again, I'll just go one by one, right? Left to right, phosphorus comes first, so let's start with phosphorus. So I have 2 phosphoruses, and I have 1 phosphorus, so I'm going to put a 2 to balance the phosphoruses, right? We said we're going to save oxygen for last, so now do the hydrogens. I have 2 hydrogens, and now 6 hydrogens. So to balance the hydrogens, I would put a 3 in front of the water. And now we can go and check our oxygens. And so when the compound, or when the element is in multiple compounds on the same side, I have to add them together, right? So all the oxygens on the reactants have to be equal to all the oxygens on the products. So I have 5 oxygens from the P2O5. I have 3 oxygens from the water, so that's 8. And then I have 2 times 4. I have 8 oxygens on the product side. So 5 plus 3 is 8. So, like I said, very often when you get everything else balanced, the oxygens will kind of fall into place. And so the oxygens are balanced, and we're done with this equation. All right, so one last example. And this is an example of a combustion reaction. In combustion reactions, you'll recognize when we have a hydrocarbon, so something that just contains carbon and hydrogen, these are often very flammable, right? And so they will readily react or burn in the presence of oxygen. And the product of combustion reactions is always carbon dioxide and water. And so I point this out just because this is a type of reaction that we'll sometimes see a lot. And so my general strategy is for these combustion reactions, right? Because oxygen appears all over the place. Again, I'm going to save the oxygen for last, right? I'll balance the carbons and hydrogens first, then worry about the oxygen. So for carbon, I have 2 carbons on the reactant side. I've got 1 on the product, so I need to put a 2 there to balance the carbons. I have 6 hydrogens versus 2 hydrogens, so I need to put a 3 in front of the water. And now I can do the oxygens. So I want to know how many total oxygens I have on the product, and that'll tell me what coefficient to use for the oxygen. So I've got 4 oxygens here, 3 oxygens here. 4 plus 3 is 7. And so you can see this is another even-odd problem, right? I have an odd number of oxygens on the product side, right? There's nothing, or at least no integer that I can multiply by oxygen that's going to give me an odd number. And so when I see this, oftentimes the easiest thing to do is I've got everything else balanced, right? I'd already balanced the carbons and the hydrogens. So to not get them unbalanced, what I can do is if I multiply all my existing coefficients, so the 1 here for the C2H6 and the 2 and the 3, if I multiply everything by 2, that's going to make everything even, and so then I should be able to balance the oxygens. So what I like to do is say, all right, we're going to put a 2 in front of there. Right, we're going to double this, so 4 and 6. Right, so the reason I doubled all the other compounds, right, is because the carbons and hydrogens are going to stay balanced. Right, now I have 4 carbons and 4 carbons. I have 12 hydrogens, and 2 times 6, I have 12 hydrogens. Right, so by doing this, I didn't mess up the carbons and hydrogens that were already balanced. And now, right, if I do this math again, I have 4 times 2 for the carbon dioxide, so that's 8 oxygens. I now have 6 oxygens for the water, so that's going to give me 14. And so now I have an even number, and so now I can balance the oxygens by putting a 7 in front of the O2. All right, so there's lots more practice in the textbook. I've got a bunch of links with good websites for practice. And so if you're not feeling 100% comfortable, try practicing on those websites, or reach out to me and we can set up a time to meet to go over some additional equations together.